This is Jack Jackson. We're going to continue our talking a little bit about parallel lines in this video. Um, it turns out that there's a extremely important um, theorem in Euclidean geometry called dealing with transversals to parallel lines. Okay, and we're going to be talking about that in this one here. So first of all, what's a transversal? So here's the definition. Given a pair of distinct lines L and M, a transversal to the pair of lines L and M is a line T that intersects both L and M. Let's go ahead and add one more thing. Let's make these lines coplanar. So given a pair of distinct coplanar lines L and M, a transversal to the pair of lines L and M is a line T that intersects both L and M. So without loss of generality, that's what WLOG is abbreviation for, we may choose points A, B, C, D, W, X, Y, and Z such that L is AB, line AB, M is line CD, N is line XY, X is between A and B, Y is between C and D, and A and B are on the same side of the transversal T. Now that's a mouthful, um, but remember when we're doing geometry, you have to be able to uh, not just look at a picture and say, oh yeah, this is how it's set up. You have to be able to adequately describe that. And so doing that, you kind of have to do all this to be able to basically get this picture. Okay, so here is our setup where we have two lines. These are the two given lines, line AB, line D. We have a transversal T, that's this line, say XY, and it intersects each of these lines. Intersects line AB at X, intersects line CD at Y. We want X to be between A and B. We want Y to be between C and D. We want A and C on the same side of the transversal, B and D on this side, and we'll put W out here so that it's on this side of this line and out here. So we have the betweenness relationship W dash X dash Y dash Z. All right, well, why do we do all that? Well, it's so that we can talk about angles, right? So we can name some angles. So angle 1 or A1, angle 1 is going to be this angle here, which is angle BXW. We'll let angle 2 be the sort of upper left angle here, angle WXA, and then go on around this first point X to get the next angle. Angle AXY is angle 3. Angle 4 is angle W or angle YXB. And then we'll go down here, kind of go in the same order, starting in the kind of like the first quadrant going, like we label quadrants, right? Going around this way. So it's kind of like we did here, 1, 2, 3, 4. And then we'll do the same thing down here, starting with 5. So angle 5 is angle WYD or XYD. Angle 6 is the angle XYC. Angle 7 is this angle CYZ. And angle 8 is angle ZYD. Okay, so notice that we have 8 angles formed. Okay, but one thing you should notice right away is, potentially that's 8 different measurements. Well, it's not, because vertical angles are always congruent. It doesn't matter which geometry we're in, vertical angles will be congruent here. So these two blue angles, angle 4 and 2 are congruent. Angles 1 and 3 are congruent, they're vertical angles. Angles 5 and 7 are congruent, and angles 6 and 8 are congruent. So you could have potentially at most 4 different angle sizes, although it's possible to get this to go down to only, uh, so you could go down to 3 angle sizes, you could go down to 2 angle sizes, and you could actually go all the way down to 1 congruence class of angles there, depending on how these sides meet. So let me go to here is the same thing in hyperbolic geometry, the same labeling, the same setup. Once again, the angles with the same color markings are the same size, right? They're congruent. Angle 1 and 3 are congruent. Angle 2 and 4 are congruent. angle 5 and 7 are congruent, and angle 6 and 8 are congruent. Now, there's the link to my GeoGebra activity, and I'm going to pull that up. You can also find it in my GeoGebra collected resources when we look at parallel lines. And it's this first one here in this, and I'm going to open it in the app once it gets going here. Let's see if I can just go ahead and so this is going to be coming up here, and there's this. So this is the general Euclidean situation here, and you've got at least those angles I've got marked. I didn't mark the ones down here, but these could be, um, well, they could be intersecting lines like that, or on this side, they could be parallel, possibly. Uh, if they happen to be, uh, so again, potentially 8 angles there, but potentially at most only 4 different angle sizes. If this is a right angle, let's see, maybe like that, then all 4 of these would be the same, but these 2 would be different. So that's 3 different angle sizes. Turns out if they're parallel, you only get 2 angle sizes. And if they're both perpendicular, then they're all right angles, and you only get 1 angle size. So there we can have that. At some point there is a right angle. I don't know if I can get it exactly, but it's pretty close right there. Right angles where they're all the same. Okay. Turns out that if you could put them just parallel, look what happens. See how these are the same? The green ones and the red ones are the same, and the blue ones and the purple ones are the same. And it turns out there's one sweet spot where that happens, and it turns out that's exactly when they're parallel. So here's the parallel situation. Let's take away that one and force them to be parallel. Now all the ones that are the same size or same color are the same size, right? They're the same measure, they're congruent. This particular case, A is a control point, X is a control point, and then this one is also a control point here. I guess Y, I guess, the way we've got it. Okay, but notice that the purple line is parallel to this. And of course, in Euclidean geometry, you know there's only one such line. So we're going to be looking at that in some detail. Here's the hyperbolic half-plane edge. Here's the general situation in hyperbolic geometry. The transversal is this line right here. This line is right now it's parallel to this line. Still parallel, not parallel, not parallel, parallel. Okay, and we're getting all kinds of different angle measurements here. So we may come back and look at that. Okay, so with this setup, we see that there are 8 proper angles formed, and we're going to name them in this way, like I've already done. Angle 1 is angle WXB, angle 2 is angle WXA, angle 3 is AXY, angle 4 is angle BXY, and so forth, so that we can name all of them by a single number this time instead of, we can't use a single letter because there's 4 different, at least 4 if you don't count the straight and 0 angles. There's 4 angles at X and at Y. Okay, so we can't just say angle X or angle Y. It gets cumbersome to talk all of these letters. So we're just going to call them angle 1, angle 2, angle 3. Well, there's lots of different pairs of angles, right? So the first thing is you have supplementary pairs, 1 and 3, 2 and 4, 5 and 7, and 6 and 8. Okay, and if you remember going back to our picture, those are the ones that are the same color there, and they are vertical angle pairs. You don't just have a vertical angle, you have a pair of vertical angles, and a pair of vertical angles are always going to be congruent to each other. Now, if you sort of draw a circle around one of these vertices, X or Y, and then look, um, then we can talk about which ones are interior and exterior, right? So if you're looking at it like this, you could draw a circle here, okay, that contain these vertices, and so basically the angles whose interiors don't include this region between, you know, X and Y, then those are called exterior angles. In other words, the outside angles, that would be A1, A2, angle 1, 2, 7, and 8 are called exterior angles. Angles 3, 4, 5, and 6 are called interior angles. Okay? You have alternate interior angles would be A3 and A5, or A4 and A6. So you have two pair of alternate interiors. You have two pair of alternate exterior angles. That would be A1 and A7, and then A2 and A8. You have a pair of, let's see, it's alternate interior, alternate exterior. You have angles on the same side of the transversal, like angles 1, 4, 5, and 8 are on the same side of the circle of the transversal, and the others are on the other side. So we would say, for example, that A1 and, of course, A1 and A4 are adjacent angles on the same side of the transversal. A5 and A8 are also adjacent angles on the same side of the transversal. We could also say, for example, that A1 and A8 are exterior angles on the same side of the transversal, as are A2 and A7. A4 and A5 are interior angles on the same side of the transversal. A3 and A6 is another pair of angles that are uh, interior angles on the same side of the transversal. And then finally, we can talk about corresponding angles. So if you like, take this point X, if you go upper right, then you're looking at the angle 1. And if you look at part at Y, the upper right is angle 5. So angle 1 and angle 5 are corresponding angles. Similarly, angle 2 and 6 are corresponding angles. Angle 3 and 7 are corresponding angles. And angle 4 and angle 8 are corresponding angles. Let me show you another GeoGebra sketch here that's useful here. This one here is dealing specifically with parallel lines, but let's take a look at it because it can point out a few things. So let's see what this does. That rotates it around. This allows us to move things around. I can move that up and down. Okay. In this particular case, we're always parallel for these lines. So there's a pair of corresponding angles. These are alternate interior angles. That's one pair. There's another pair right here and right here. There's another pair. There's actually four pair of corresponding angles. That's two of them. And then here we have that. Okay, what do we know? Alternate exterior angles would be those two, or what? This one and this one, right? Same side interior angles would be that. And same side exterior angles would be like those two. And these are not the only pairs, but they're just some of the pairs. When they're parallel, what do you notice here when you look at this? What about these corresponding angles? Whenever I manipulate this around. Oh, that's interesting. What do you notice? Do you notice that they're congruent? How about these? Right? It looks like they might be congruent there as well, or the alternate exteriors. However, the ones on the same side of the transversal, like that are on the interior, they're not They're not congruent, but they also have a special relationship. Can you see what it would be? Oh, look at that. Looks like they are what? Supplementary. Okay, so that's kind of some interesting things. So here in the notes, I've written down which pairs are corresponding pairs, which ones are interior, which ones are exterior, which ones are alternate interiors, alternate exteriors, interior angles on the same side of the transversal, exterior angles on the same side of the transversal, and so forth. Okay, so let's look at what we got. Because the congruent pairs of vertical angles, the A-proper angles formed have at most 4 different measurements. Sometimes this can be reduced to 3, 2, or even only 1 measurement. We can only get 3 measurements. We get only 3 measurements if the transversal is perpendicular to one of the lines, but the other is not perpendicular. There's only 1 measurement, pi over 2 radians, 90 degrees, if and only if the transversal is perpendicular to both of the lines. And there can also be a situation, however, there's only 2 measurements. And this situation can occur when all the angles that are labeled with even numbers in our picture are congruent, and the odd labeled ones are also congruent. And then it turns out that all the odd labeled ones are congruent, even labeled ones are congruent if and only if the lines are parallel. Now that last statement, that's only half true in hyperbolic geometry. Okay? That's an if and only if statement. That's two statements, 2 conditional statements. One of those is true in hyperbolic and the other one's false. Can you figure out which one's which? You might pause the video and think about that a second. And but it's true. It is true in one direction in Euclidean and hyperbolic geometry. Since this only deals with parallel lines and angles, doesn't say anything about lengths of things, the result is exactly the same for Euclidean and taxicab geometries. Okay. In spherical geometry, we're going to write a theorem down. Technically, it's true, but the first line of the sentence is going to say, it's going to assume that we have an unbounded metric, which basically just eliminates spherical geometry. There's no such thing as a parallel line in spherical geometry. Okay? Now, we're going to have different parts of this. The first part follows directly from the vertical angle theorem, which is true in spherical geometry as well. And then we prove the z property. For the other parts, we know that if their hypothesis is true, the hypothesis of the z property is true, and we apply the z property to reach the conclusion. So the crux of the matter is proving the z property, which works in one direction for hyperbolic geometry, works in both directions for Euclidean geometry. So remember, proof in geometry must stand on its own without reference to any illustration. So we need this first paragraph here to set everything up. Unfortunately, it's rather cumbersome. In my class, I'll just sort of provide you with that first paragraph so you don't have to mess with that. But basically, you boil down to getting that paragraph, then you get this illustration here. Okay? Now, ultimately, we're going to be in the parallel situation, so it's going to look like this. Okay? Now, by the way, let's talk about what these, well, we'll come back to that in just a second. Let's go down to here. So the first part is just setting it up. Then we say, of the 8 proper angles that are formed by the transversal and one of the other lines, they have at most 4 different measures because each angle is congruent to at least one of the other angles. Specifically, vertical angle pairs are congruent. Angle 1 is congruent to 3, 2 is congruent to 4, 5 is congruent to 7, and 6 and 8 are congruent. And each one of these angles is supplementary to at least 2 of the other angles. Okay, the ones at the same vertex that are not a vertical pair are always going to be either a linear pair and they're supplementary, or they're going to be vertical to each other and then they're going to be congruent. That's a basic property from what we've learned before, so not really much new to prove there. Now, these letters that I use, Z property, C property, F property, I picked that up somewhere along the line, but they are not necessarily completely standard letters, but they're pretty useful. Why do they do this? So here, if you can look at the picture right here, you can kind of see why we would call this the Z property. if you can kind of see the letter Z, and these angles here are the ones we're talking about. Now this Z may be upside down and maybe reflected over whatever, but it's a basic letter Z, and we're saying what we're looking at is a pair of alternate interior angles. And so the Z property in neutral geometry, this works in hyperbolic as well as Euclidean geometry, says if we have a pair of congruent alternate interior angles, then the two lines have to be parallel. In Euclidean and hyperbolic geometry, right here, the first thing says let the distance metric be unbounded. That eliminates spherical geometry from our conversation. Again, remember, there are no parallel lines in spherical geometry. All right. How about the C property? Here's the letter, it's kind of like a letter C here. So now we're talking about these angles. These are interior angles on the same side of the transversal. And if it turns out if they're supplementary, then the two lines are parallel. Okay. If a pair of alternate exterior angles, like here and here, don't have a letter to go with that one, but if those are congruent, then the two lines have to be parallel. If a pair of exterior angles on the same side of the transversal are supplementary, then L and M are parallel, here and here. And an F property, see the letter F there? If these two angles are congruent, those are corresponding angles, or any other pair of corresponding angles are congruent, then L and M are parallel. And then the next thing to notice is if the hypothesis of any of these parts from B to F, if any one of those true, then they're all true. Okay, and so what we have is the measures of all the red angles are the same size, and the measure of all the blue ones, well, all the odd numbered ones, the way we've done it, and are congruent, and all the even ones are congruent. They all have even congruent angles, equal measures. So let's just kind of see if we can talk about that last part first. Okay, so if let's just take any one of these. Let's say that the Z property. Let's see, where's our letter Z? Zip, Z. It's these red ones, say A3 and A5, or A5, 4 and A6, either one of those. A pair of alternate interior angles are congruent. Well, if they're congruent, notice that the other pair of alternate interior angles are congruent because they're just supplementary to those. So now, and if that one's congruent, then these are two are congruent because the two blue ones here and the two blue ones are here are congruent. So that makes all the ones labeled as blue, the even labeled ones, 2, 4, 6, and 8 are all congruent. And that makes all the odd ones congruent as well by the same argument. Here's the situation, the sort of the Z parallel situation, I call it, in the hyperbolic geometry, where you have a pair of alternate interior angles are congruent, say the A4 and A6 or A3 and A5. If you get that, you get all that's set up the same. If you've got a pair of, let's see, so that's the hypothesis Z. What about the hypothesis of C? If you know that, say, A4 and A5, that's like there's your C. If they're congruent, no, not congruent, those are supplementary. So if those are supplementary, then remember A3 is also supplementary to this, right? And that's going to make A3 and A5 congruent. Now this is Z property. Now we got all of our congruent pairs. So we got our two sizes of angles. What about if you have the hypothesis here, alternate exteriors? Okay, that would be like, which ones? Like A1 and A7. Well, if A1 is congruent and A7 are congruent, remember A5 and A3 are in the same congruence class too. Now we've got the Z property, and we get all the pairs of angles are congruent that we have there are two congruence classes, two supplementary classes there. Exterior angles on the same side are supplementary. Okay, exterior on the same side. That would be like A1 and A8. If those are supplementary, then let's see, then this one, then these two inside are supplementary. We already showed that's enough to make our pairs. And F, a pair of corresponding angles are congruent. Let's see, where's our F? Here's our letter F. So we're talking about A4 and A8, for example, or any other corresponding pair like A1 and A5 or A2 and A6. If you get one pair corresponding, one congruence, all the corresponding pairs are congruents. Okay, and I think you can chase through that and see that pretty easily. So in light of this part here, we sort of prove that part first. Okay, then what we notice is if you got any one of these hypotheses up here, you have all of them, right? So we just have to prove one of these gives us parallel lines, and then we prove that all of them give us parallel lines. So the key is going to be the z, right? The z property right there. If we can get that to prove that we have parallel lines, then the C property is going to give us parallel lines and all these other different ones here. And this proof is going to work in Euclidean and in hyperbolic geometries. Since it works in Euclidean geometry, it's going to work in taxicab geometry as well. Okay, so there's our basic setup. Okay, and then I prove part G next. And now here is the proof of the Z property. And this right here. This is going to be a very important proof. Okay, we're given a pair of alternate interior angles are congruent. We've shown that the other pair of alternate interior angles are also congruent. So angle 3 is congruent to 5 and angle 4 is congruent to 8 in our diagram, right? Suppose that the pair of lines L and M are not parallel. So this is going to be a proof by contradiction. They got to intersect at a point P. Okay, so let me draw that. I can't really draw it correctly here because it's a situation that doesn't exist. But let's draw it and let's show that they're not parallel and that there's a point P where they intersect. Let's go ahead and find that point of intersection. And let's call that guy, let's call him P. Okay, now we're assuming, which is not true in this picture, right? Because we can't draw it that way, it's impossible, that the alternate interiors A3 and A5 are congruent. Okay, but now what do you notice? What do we have right here? We got a triangle, right? It's either going to be on this side or it's going to be on this side. But either way, either A3 and A5 are congruent or A4 and A6 are congruent. Well, you know that they're both things happen. So whichever way you look at it, one of A5 and A3 is an interior angle of this triangle, and the other one's an exterior angle. If they meet on this side, it's the other way around. A3 is the exterior angle, A5 is the interior. On this side here, P's on this side, A3 is an interior, A5 is an exterior. Either way you go, what do you have? You have an exterior angle that's congruent to an interior angle. Again, they're not in this picture because it's impossible to draw. But that is an impossible situation because that contradicts the exterior angle theorem. Now, by the way, right there is where the proof breaks down for spherical geometry, right? Because in spherical geometry, the exterior angle theorem is not, exterior angle inequality theorem is not true. Okay? But we've reached our contradiction. So here's the proof. Suppose the pair of lines are not parallel. They must intersect at a point P. We form the triangle XYP. Notice that P is on the same side of the transversal as B. That angle 3 is an external to this and triangle, and angle 5 is a remote interior angle. And the other way around, if P is on the same side of transversal A, then it just switches. In either case, we have an external angle with the same measure as remote interior angle. This violates the external angle theorem, inequality theorem. Therefore, our assumption must have been false, and the two lines have to be parallel. So it's not too hard of a proof. It is a little proof by contradiction. It uses the exterior angle inequality theorem. That's a major step. So it's really important that we can prove that external angle inequality theorem, which we did in our last playlist, our last chapter. And so now that we have that, we proved the Z property. And notice that there's nothing in this that's violated in neutral geometry. Okay, and this is not going to work. And of course, we knew this is going to be false in spherical geometry because what happens here? We can do a situation in spherical geometry where we have alternate interior transversals and alternate interior angles are congruent, but we know there's no parallel lines in spherical geometry, so there's no way this is going to work. And the proof breaks down when we try to use that exterior angle, external, it should be exterior angle inequality. Okay, so what about the converse of this? That's the thing we should be asking ourselves. Well, it turns out the converse of this theorem is true in Euclidean geometry. We'll prove that in the next video, but it's false in hyperbolic geometry. In hyperbolic geometry, we take a line, a point, and a line, and make the parallels of the given line through the point. We can draw the transversal from a point on the given line through the given point, not a line. And this will be a transversal to infinitely many pairs of lines. However, only one of them will have congruent alternate interior angles. Okay, so if we look at back here, let's see what I've got here. Let's look at the Euclidean parallel situation. There's the Z, there's the F, there's the C. Okay, let's look at the hyperbolic situation. There's the general situation. Here's the Z situation. So let me do this. So here we have a line here. This one's free to move anywhere we want. And here we pick a point here that we can move around. But the rest of it's fixed, so that we pick the transversal is the line XY. And we fix it so that the interior angle here has the same measure as the interior angle here, alternate interior angles, the Z property, or these two red ones here. And sure enough, we get all the angles, the two congruence classes of angles there, just the two angle measures. And then this purple one will always be parallel. But here's the deal. That's not the only one that we can have. One of these is able to move. So that one's also parallel, and you see clearly the angles are different there. So there's lots, of course, some of these are not parallel. That one's not, but there's lots of parallel ones right in here that go through that same point Y. Let's see, that's parallel, 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 parallel. And these angles are changing, right? So there are infinitely many parallels. Because there's so many more parallels, the Z property only works in one direction for hyperbolic geometry. The Z property does work in the sense that, in the direction that if you have a pair of angles here that are congruent, that are alternate interior, like 3 and 5 or 4 and 6, then in fact these two lines do have to be parallel, the original line here and then the purple one here, and you just get the two sizes of the angles here. But in hyperbolic geometry, there are many other parallels that don't have that. So just because they're parallel doesn't make the alternate interior angles congruent. So the hyperbolic property works in one direction only. All right, we'll come back and prove the situation in the other direction, okay, for Euclidean geometry in the next video.